Have you ever looked up at the night sky and felt a sense of profound silence? That cold, quiet emptiness that stretches out into infinity? For most of celestial history, we've understood that silence. We've learned its rules, its rhythms. We know that in the frigid depths of space, far from the life-giving warmth of a star, things are supposed to be still, dormant, frozen. But what happens when something out there breaks that silence? What does it mean when a lonely wanderer from another star system, a traveler through the deep dark, suddenly seems to take a breath? Right now, an object named 3I Atlas is doing just that. It is a comet, a visitor to our solar system, and it is exhaling a torrent of water into the freezing void, 40 kilograms of it, every single second. This isn't happening near the sun, where we'd expect such a show. No, this is happening out in the cold, a place so distant that our own comets are little more than lifeless, sleeping rocks. The astronomers who watch this ghost-like plume unfurl from its surface are whispering a word they almost dare not say. It's acting alive. But the story of this impossible comet, this traveler with secrets, is only just beginning. It carries with it strange chemical fingerprints, like nickel, without a trace of its cosmic partner, iron. Its tail is laced with cyanide, and its very trajectory hints at an origin story billions of years older than our own sun. Is this just a cosmic anomaly? A beautiful, baffling fluke of nature? Or are we witnessing a messenger, a vessel carrying news from a corner of the galaxy so different from our own that it forces us to question the very rules we thought we understood? Just imagine for a moment you're floating out there with it, in that perfect, cold silence, more than 3 times farther from the sun than our Earth is. Out here, the sun is just another bright star in the tapestry of the cosmos. Its light is a mere whisper, its warmth a distant memory. In this realm, ice doesn't melt. It stays locked in a state of suspended animation for eternity. Comets, those dirty snowballs of the solar system, go into a deep hibernation. Everything sleeps. And then, through the blackness, you see it. A comet that is not sleeping. You see 3I Atlas, and it is absolutely hemorrhaging water into the void. This isn't a gentle mist or a subtle trickle. It's a flood. Think about it, 40 kilograms of water pouring into space, second after second after second. That's like taking a small car, turning it into pure water, and dumping it into the vacuum of space every single minute. This colossal fountain is erupting from a frozen rock where, by all accounts, water should have no business flowing at all. This is the heart of the mystery. The first clue that 3I Atlas is something special. It's an interstellar comet, a relic that arrived in our solar system from somewhere else entirely, from the backyard of another star. And it seems to have brought with it a different set of rules, a playbook for cosmic behavior that doesn't match ours in the slightest. The first real glimpse of this impossible activity came from a space telescope called SWIFT. SWIFT wasn't even designed to look for comets. Its primary mission is to hunt for the most violent explosions in the universe gamma-ray bursts. But when astronomers turned its sensitive ultraviolet eyes toward 3I Atlas in early 2025, they saw something that simply shouldn't have been there. They detected a vast, glowing halo of molecules called hydroxyl surrounding the comet. Now, hydroxyl, or O, is what you get when the harsh ultraviolet light from the sun finds a water molecule and brutally rips it apart. It's the chemical echo of water screaming as it dies. When you see a cloud of hydroxyl, you know, with absolute certainty, that a massive amount of water was just there. And SWIFT saw a lot of it. The sheer scale of it is difficult to wrap your head around. The data showed that at a staggering distance of 3.51 astronomical units from the sun, that's more than 3, and a half times the distance from the Earth to the Sun 3, I Atlas was furiously releasing 1.35 times 10 to the power of 27 water molecules every single second. That's the calculation that gives us that mind-bending figure. 40 kilograms per second. To truly grasp how bizarre this is, you have to understand our own comets. The comets born in our solar system simply do not do this. Not out here in the cold. This far from the sun, they are practically dead. They are cold, dormant chunks of ice and rock, waiting patiently. Water ice needs a significant amount of heat to sublimate, which is the magical process where a solid turns directly into a gas without ever becoming a liquid. It's what gives comets their beautiful, streaming tails of gas and dust. But that process requires energy, and there is simply not enough solar energy this far out to drive that kind of intense activity. Our comets have to wait. They wait until they swing much, much closer to the sun before they finally wake up from their long slumber and begin to stream their contents into space. Clearly, 3I Atlas didn't get that memo. This behavior sets it apart from every other interstellar visitor we've ever had. You might remember our first confirmed guest from another star, the mysterious object we named Oumuamua. That thing was a complete enigma, but in the opposite way. It was as dry as a bone. There was no water, no outgassing, just a strange, tumbling, cigar-shaped rock speeding silently through our neighborhood. It was a ghost. Then came our second interstellar comet, 2I Borisov. Borisov was active, sure, but it behaved exactly as our own comets do. It followed the script. It was predictable. In a way, it was wonderfully boring, because it confirmed that the comets in other star systems could be just like ours. 3I Atlas is neither of those things. It's not silent, and it's certainly not predictable. It is alive in a way that feels impossible, screaming water into the void where only silence should reign. And this one simple observation, this impossible fountain of water, has left a single, profound question hanging over every astronomer who has pointed a telescope at this celestial phantom. How? What incredible mechanism could possibly be driving this? Is there some kind of exotic ice we've never seen before? Something that sublimates at temperatures we thought were far too cold to sustain such activity? Could the comet's interior somehow still be warm, holding on to the residual heat from its violent birth billions and billions of years ago? Perhaps it's rotating in some bizarre, complex way that focuses the faint sunlight onto hidden pockets of volatile materials, like a cosmic magnifying glass. Or, and this is the most tantalizing possibility, is there a type of chemistry happening deep inside that rock that we have simply never encountered before? The water, as staggering as it is only the beginning of the mystery. 3I Atlas is leaking other things too, strange things. Each new observation, each new spectral line that shows up in the data, adds another layer to the enigma, another question mark on the board. This isn't just a comet behaving oddly. This is a comet that seems to be operating under a completely different set of physical rules, rules that were written in another star system, under different conditions, with a different kind of chemistry. And now, it's here, in our solar system, giving us a front row seat to cosmic processes we've never, ever seen before. The thing that is truly keeping astronomers up at night is what this all implies. If 3I Atlas can do things our comets can't, what does that tell us about where it came from? What kind of star system builds comets like this? And perhaps the most provocative question of all, is this comet just a beautiful cosmic weirdo? Or is it something more? Is it a messenger, carrying news of just how incredibly different and wonderfully strange the rest of the universe can be? Right now, every telescope that can see this thing is pointed at it, trying to unravel its secrets. Because 3I Atlas isn't just a curiosity. It's a window, a tiny crack in our understanding of the cosmos. And through that crack, we might just glimpse something absolutely extraordinary. That impossible plume of water, screaming into the void where silence should reign, was the first sign that 3I Atlas was a visitor from a very different place. It was the opening chapter in a story that was just beginning to unfold. The first clue that this comet was not playing by our rules. But as astronomers stared harder, using every tool at their disposal to dissect the faint light from this distant wanderer, they found something else. Something that, in its own way, was even more baffling than the water. It was an anomaly so fundamental that it felt like finding smoke without a fire, or footprints in the sand without feet to make them. It was a discovery that challenged not just our understanding of comets, but the very chemistry we've come to expect from the cosmos. You see, comets, like everything else in our system, are supposed to follow certain patterns, certain predictable recipes. When they get close enough to the sun and begin to heat up, the metals locked within their icy bodies start to sublimate and escape into the coma, the glowing atmosphere around the comet's nucleus. And in our corner of the galaxy, two metals in particular always show up together, iron and nickel. They are like old friends, cosmic twins who travel in inseparable pairs. You see one, you always see the other. It's one of those cosmic constants we've come to rely on, a foundational rule written in the textbook of our solar system. Except 3I Atlas, it seems, never bothered to read that textbook. Deep in the Atacama Desert in Chile, a team of astronomers aimed one of the most powerful eyes on Earth, the aptly named Very Large Telescope, at the faint smudge of 3I Atlas. They weren't just taking a picture. They were performing a kind of cosmic autopsy. They used an instrument called a spectrograph, which takes the comet's light and splits it into its constituent colors, a rainbow barcode of its chemical composition. And as the data streamed in, something appeared that made them lean closer, check their instruments, and question what they were seeing. Blazing bright in the spectrum, as strong and unmistakable as a lighthouse beam in a fog, were the emission lines for nickel. The signature was impossible to ignore. But where was its partner? Where was the iron? It was either completely absent, or so vanishingly weak that it barely registered on their sensitive instruments. Nickel without iron. In our solar system, this simply doesn't happen. When a comet heats up enough to start releasing metals, iron and nickel appear in predictable ratios because they are born from the same processes, locked together in the same mineral structures. They sublimate at similar temperatures. They are chemically bonded in ways that keep them perpetually paired. But 3I Atlas, this messenger from another place, appears to have formed somewhere that plays by an entirely different set of chemical rules. The data was precise. At a distance of around 2.8 astronomical units from the sun, still far out in the cold, but closer than where the water plume first erupted, astronomers measured nickel pouring off the comet at a rate of about 5 grams every second. Now, 5 grams might not sound like much. It's about the weight of a single sheet of paper. But imagine that piece of paper appearing out of thin air, second after second, hour after hour, day after day, all with its fundamental counterpart, iron, nowhere to be found. That's not a glitch in the data. That's a pattern. That is the comet telling us something profound and strange about its very makeup. This single observation has sent a shockwave through the astronomical community, forcing scientists to scramble for explanations. None of them are simple. The first possibility they've considered is a process called chemical fractionation. Just imagine the chaotic, swirling cloud of gas and dust where 3I Atlas was born, billions of years ago. Perhaps in that unique environment, nickel had a tendency to get incorporated into extremely volatile compounds, things that vaporize very easily. Picture nickel hitching a ride with lightweight, eager-to-escape ices, while iron, by contrast, got locked away into more stubborn, refractory minerals that need much higher temperatures to sublimate. It would be a chemical sorting process, where nickel was primed for an early escape, leaving its iron sibling behind in the rocky grains. Another, even more exotic idea involves something called organometallic compounds. Here on Earth, we can create molecules like nickel carbonyl, where individual nickel atoms bind to molecules of carbon monoxide. These compounds are incredibly volatile. They evaporate at relatively low temperatures. What if 3I Atlas formed in a place that was unusually rich in carbon monoxide and other organic materials? Maybe, just maybe, the nickel got trapped inside these special molecular packages. Then, as the comet approached our sun, the faint sunlight was just enough to break these packages apart, releasing a cloud of atomic nickel into the coma, while the iron remained firmly locked away in its solid, rocky prison. Then there is the effect of its long, lonely journey. An interstellar object like 3I Atlas has been wandering the galaxy for millions, perhaps billions of years. Over that immense timescale, it has been constantly bombarded by cosmic rays and seared by the ultraviolet radiation from countless stars. This sustained, brutal assault is known as space weathering, and it can alter the surface chemistry of an object in very strange ways. Could it be that this radiation processing created a unique, nickel-rich surface layer? A kind of radiation-damaged rind that doesn't reflect the comet's true bulk composition? Perhaps the iron is still there, but it's been buried deeper inside or chemically altered by eons of radiation, hidden beneath this strange nickel skin. Or maybe, and this is by far the most exciting and world-altering possibility, 3I Atlas comes from a place that was just fundamentally different. We tend to think of the universe as being made of the same stuff everywhere, but it isn't. Stars are not all born with the same chemical makeup. Older stars, stars from different regions of the galaxy, stars that formed from gas clouds enriched by different types of exploding supernova, they all have slightly different elemental recipes. What if 3I Atlas comes from a star system where nickel was genuinely more abundant relative to iron than it is in our cosmic neighborhood? What if its parent star was chemically odd, and that primordial oddness is now written into every single molecule of this visiting comet? This would mean the comet is a direct sample, a physical fragment of a chemically alien star system. Of course, good science demands caution. We have to be careful here. Spectroscopy, the art of reading these chemical barcodes, is incredibly difficult. Detecting faint emission lines against the bright, fuzzy background of a comet's coma is a tricky business. There are always thresholds of detectability. It is entirely possible that the iron is there, but it's lurking just below the limit of what our best telescopes can currently see. Maybe its signal is being blended with other spectral features, hiding it from view. Maybe we are simply looking at the wrong wavelengths. There is a chance that as the comet gets even closer to the sun and heats up more, the iron will finally start to appear. In a way, that would be reassuring. It would mean the universe still makes sense according to the rules we know. But what if it doesn't? What if 3I Atlas makes its entire journey around the sun, reaching perihelion, its closest and hottest point, and the iron never shows up? What if this bizarre, inverted nickel-to-iron ratio remains a permanent feature? That outcome would be nothing short of revolutionary. It would be definitive proof that other planetary systems can produce comets with a metal chemistry so radically different from our own that our current models would need a complete and total overhaul. It would mean our cosmic textbook isn't just missing a few details. It's missing entire chapters. This is precisely why astronomers are now watching 3I Atlas with such obsessive intensity. Every new observation is a test. Every spectrum is a chance to either confirm our place in a predictable universe or shatter our assumptions about it entirely. And right now, as this ghostly green visitor continues its silent scream, 3I Atlas is doing far more shattering than confirming. The mystery of the lonely nickel, a ghost of a metal floating in space without its cosmic twin, was a profound challenge to our understanding of cosmic chemistry. It proved that 3I Atlas was built from a recipe we had never seen before. But this comet wasn't just a static collection of strange ingredients. It was dynamic, it was changing, and its behavior over time was about to reveal another layer of its impossible nature. Comets, as a rule, are supposed to be gradual creatures. Their journey toward the sun should be a smooth, predictable crescendo of activity. The physics is beautifully straightforward. The closer a comet gets to the sun, the more sunlight it receives, which means more heating. More heating leads to more sublimation, which releases more gas and dust. The relationship between distance and brightness should be a gentle, elegant curve. It should be, for all intents and purposes, almost boring in its predictability. But 3I Atlas, it seems, has no interest in being boring. As observers around the world tracked its slow journey inward, they began to notice something strange about its very appearance. Early on, when it was still far out in the frozen depths, the comet looked relatively neutral in color, perhaps tinged with a slight reddish hue, which is typical for distant, icy bodies reflecting the faint light of the sun. But as it moved closer, something began to change. It started to turn green. This wasn't a subtle shift that required complex instruments to detect. It became a vivid, eerie, unmistakable green that blossomed in long exposure photographs, a ghostly emerald glow against the black velvet of space. What was causing this dramatic transformation? That green light comes from two specific sources we've already met: cyanide molecules and those strange, lonely atoms of atomic nickel. Both of these substances, when excited by sunlight, emit light very strongly in the green part of the spectrum. And as the comet warmed, the signatures of both cyanide and nickel didn't just appear. They began ramping up dramatically, as if someone had slowly turned up a celestial dimmer switch. But even that description doesn't do it justice. The brightness increase wasn't just linear. It wasn't a smooth, steady climb. Astronomers describe it as superlinear, which is a wonderfully scientific way of saying that the comet was intensifying far faster than our simple, elegant physics could predict. To understand why this is so strange, you have to remember a basic law of physics called the inverse square law. It sounds complicated, but it's simple. If you have your distance to a light source, the light you receive is 4 times brighter. It's a fundamental rule of geometry. As 3I Atlas got closer to the sun, it was indeed receiving more light, but its emissions, that green glow from its gas and dust, were climbing even faster than that. It was as if the comet had an internal engine that was kicking into a higher gear. Something new was being unlocked. Some new process was being ignited. This is what astronomers call switch-on behavior, and it is one of the most fascinating and mysterious aspects of this interstellar visitor. Imagine the comet as a series of hidden temperature thresholds. Below a certain threshold, a particular type of ice stays perfectly solid, locked away deep inside the nucleus, completely dormant. But then, as the comet travels, it crosses that invisible line in space. The temperature rises just enough, and suddenly, that specific ice begins to sublimate with explosive force. The gas production jumps, and brand new emission lines, new chemical fingerprints, suddenly appear in the spectrum. It is exactly like flipping a switch. One moment, the process is off. The next moment, it's fully on. And once that switch is flipped, if there is enough material to feed it, the reaction can run away with itself, creating a dramatic surge in activity. 3I Atlas appears to have multiple of these switches, each one tied to a different component of its alien chemistry. The water, as we know, was the first to turn on, way out at 3.5 astronomical units, a distance that was already anomalous. Then, as it warmed further, came the cyanide and the nickel, blazing with that ghostly green light. Each new emission suggests that a different volatile reservoir is being tapped into. A different chemical environment buried within the comet is reaching its unique activation temperature. How could this be happening? One of the most compelling models to explain this behavior involves something called extended icy grains in the coma. Instead of imagining all the activity happening right at the surface of the comet's nucleus, picture this. As gas escapes from the nucleus, it lifts tiny microscopic grains of ice off the surface with it. These little grains float away from the comet, drifting in a cloud, still frozen, still cold. But as they drift, they are individually exposed to more and more sunlight from all angles. Eventually, each tiny grain reaches its own personal temperature threshold and begins to sublimate. This creates a distributed source of gas. The comet's activity is no longer coming just from the central nucleus, but from a vast, glowing cloud of these icy, mini-comets surrounding it. That could perfectly explain the superlinear jump in brightness and the sudden appearance of new emission lines as a whole new population of material switches on at once. Another incredible possibility is thermal fracturing. Remember, comets are not solid rocks. They are fragile conglomerates of ice and dust, often described as dirty snowballs. When one part of the comet heats up and expands while another part, perhaps on the shaded side, stays cold and contracted, immense stresses build up within its structure. Eventually, something has to give. Something cracks. When the ice of a comet cracks, it can expose vast amounts of fresh, pristine material that was previously insulated deep inside. Suddenly, you have a brand new surface area exposed to the sun, new volatiles escaping into space for the very first time. The comet experiences an outburst. 3. Atlas might be literally cracking itself open as it heats, revealing layer after layer of its frozen, ancient chemistry to us. And then, of course, there are the exotic ices themselves. Water ice sublimates at one temperature. Carbon monoxide ice, by contrast, sublimates at a much, much lower temperature. Carbon dioxide is somewhere in between. If 3. Atlas is layered like a cosmic onion, with different types of ices concentrated at different depths or in different regions, then as it warms, you would expect to see a beautiful, sequential series of activations. First, the supervolatiles like carbon monoxide would switch on in the deep cold. Then, as it gets warmer, the normal volatiles like carbon dioxide and water would join the show. And finally, perhaps the really stubborn stuff, like those organometallic compounds holding on to the nickel, would release their contents. We might be watching this comet peel back its layers, one by one, like chapters in a book written billions of years ago. Now, this kind of behavior isn't entirely alien to us. We have seen comets in our own solar system do some very weird things. Some of our comets have sudden, unpredictable outbursts, brightening by factors of 10 or even 100 overnight. Some comets split apart entirely as they approach the sun, their structural integrity completely overwhelmed by the thermal stresses. But the crucial difference is that 3 Atlas is doing all of this on a schedule and at a distance that simply doesn't match our experience. It is alive and active at distances where our own comets are supposed to be sound asleep. It is switching on in a sequence that feels almost deliberate, almost choreographed. And so, the tension among those who watch it is building. As 3 Atlas continues its relentless journey inward, toward its closest encounter with our sun, what other switches are waiting to be flipped? Will we see brand new emission lines appear in its spectrum, revealing molecules we never expected to find? Will its activity eventually plateau, or will it continue to accelerate in this runaway fashion? Every single week brings new data, new surprises. This is not the steady, predictable wanderer we thought we knew. This is a cosmic drama, unfolding in real time, right above our heads. This comet, 3 Atlas, with its impossible water plume, its lonely nickel, and its choreographed series of awakenings, was clearly more than just a rock. It was a puzzle box, a visitor carrying a complex and layered mystery. But every object in space, no matter how strange, carries another, more fundamental story with it, a story written not in chemistry, but in motion. Its trajectory, the path it carves through the fabric of space-time, is a perfect footprint. And by following that footprint backward, we can learn not just where it is going, but where it has been. For 3 Atlas, that footprint is telling a story that may span not just thousands of light years, but billions of years, pointing back to a time before our own solar system was even born. The first thing astronomers noticed about its path was its shape. The orbit is what's known as hyperbolic. That's the technical term for an open curve, a path that doesn't loop back on itself, like the elliptical orbits of our planets and local comets. It means that 3I Atlas came from the vast emptiness of interstellar space. It will make one dramatic swing around our sun, and then it will leave again, flung back into the darkness, never to return. Its orbital eccentricity, a measure of how much an orbit deviates from a perfect circle, is greater than 1. In the language of celestial mechanics, that's the definitive signature of an unbound object, a free agent, a true wanderer of the galaxy. It is just passing through. Armed with this knowledge, astronomers began the painstaking work of detective astronomy. They traced its path backward, a process made possible by an incredible technique called precovery. Precovery is when you search through massive archives of old survey data, looking for faint images of an object that was captured long before anyone knew it was interesting. It's like finding a picture of a suspect in a crowd photo, taken years before the crime was ever committed. And it turns out, 3I Atlas had been photographed multiple times by automated sky surveys, completely unnoticed. Some of these images went back to when the comet was a staggering 6.4 astronomical units away, still inbound, still cold and distant, and just a faint pinprick of light. By stitching together all of these observations, from the earliest precovery images to the latest, most detailed views, astronomers were able to reconstruct its trajectory with ever-increasing precision. And that trajectory points outward, back into the Milky Way. But not just anywhere. This is where the story takes a truly mind-bending turn. By combining the comet's precise orbital model with the vast three-dimensional map of our galaxy created by the Gaia Space Telescope mission that has charted the exact positions and motions of nearly 2 billion stars, astronomers could do something that would have been science fiction just a generation ago. They could make a highly educated guess about where in our galaxy 3I Atlas might have originated. And the answer was as surprising as it was profound. Our galaxy isn't just a random collection of stars. It has a structure, a celestial architecture. Most of the stars we see, including our own sun, live in what's called the thin disk. This is a relatively flat, dense plane of younger, chemically enriched stars, all orbiting the galactic center in an orderly fashion. But there is another, older structure surrounding it, the thick disk. The thick disk is a more diffuse, puffed-up population of ancient stars. They orbit in more tilted, more eccentric, more chaotic paths, spread farther above and below the main galactic plane. These stars are different. They are older, formed much earlier in the galaxy's history, at a time when there were far fewer heavy elements to go around. They have what astronomers call a lower metallicity, and the trajectory of 3I Atlas, its unique speed and angle of approach, strongly suggests it might have come from this ancient population. It might be a child of the thick disk. If that is true, if this single comet was born in that ancient stellar neighborhood, then it could be significantly older than our entire solar system. Our sun and its planets formed about 4.6 billion years ago. But the stars of the thick disk can be 7 billion years old, or even older. This means that 3I Atlas could be carrying ice and rock that were formed before the sun itself even existed. It could be a physical relic from a time when our solar system was nothing more than a cold, diffuse cloud of gas and dust. Think for a moment about what that means chemically. The primordial gas cloud that collapsed to form a thick disk star 7 billion years ago was a very different place than the one that formed our sun. The universe has been steadily enriched with heavy elements over time, seeded by the explosive deaths of massive stars supernova. The very first generations of stars were made of almost pure hydrogen and helium, the raw materials of the Big Bang. Later generations, like our sun, were born from gas that had been seasoned with a few percent of these heavier elements, the stuff that makes up planets and people. The stars in the thick disk are the generation in between. They have some heavy elements, but significantly less than we do. If 3I Atlas formed in that chemically primitive environment, its composition would be a perfect reflection of that lower metallicity. There would be less iron, less magnesium, less silicon, all the rocky elements that build terrestrial planets. But there would still be plenty of the lighter, volatile elements, carbon, nitrogen, and oxygen, all locked away into ices and simple molecules. Could this be the reason for its strange chemistry? Maybe that is why we're seeing such an unusually high ratio of carbon dioxide to water. Maybe that's why the metal ratios look so bizarre. Maybe this comet is not just a visitor. It has a chemical fossil from a time when the galaxy was younger, and the periodic table was a far emptier place. Of course, we can't be absolutely certain. Tracing an object back through billions of years of chaotic galactic motion is an incredibly complex task. The gravitational nudges from passing stars, the subtle interactions with the galaxy as spiral arms, all of these things can muddle the trail over such vast timescales. But the fact that it is even plausible that the data so strongly points to the idea that 3I Atlas is older than our Sun is simply extraordinary. We could be looking at a relic, a survivor, a time capsule sent to us from the ancient galaxy. And if we could ever pinpoint its exact birth cluster, the group of stars that all formed together from the same primordial cloud, we might someday be able to identify its long-lost siblings. Other comets, maybe even rogue planets that were ejected from the very same system, now scattered like dandelion seeds across the galaxy. 3I Atlas might not be a solitary messenger. It might be just one letter in a message written across thousands of light years and billions of years. And we are only just beginning to learn how to read it. To think of 3I Atlas as a time capsule, a physical fragment from an era before our Sun ignited, is a staggering thought. It transforms the comet from a mere scientific curiosity into a sacred relic. But comets are more than just fossils of a bygone age. They are cargo ships. They are cosmic vessels, carrying a detailed inventory of the molecular building blocks present in their birth environment. And the manifest for 3I Atlas reveals it is carrying some of the strangest cargo we have ever seen. This isn't just about where it came from, but what asterisk it brought with it. And every molecule we detect is another word in the message it's delivering to our doorstep. We've already been stunned by the water, that impossible fountain gushing 40 kilograms per second into the deep freeze of space. That water, or more accurately, the hydroxyl fragments that sunlight rips from it, was the first explosive clue that this visitor was something entirely new. But as strange as the water is, it's just the beginning of the story. The real shock, the entry on the cargo list that is forcing a complete re-evaluation of how planetary systems can form, is the carbon dioxide. Our own solar system's comets have a clear and consistent hierarchy. Water is king. It is almost always the dominant volatile, the primary engine driving a comet's activity as it nears the Sun. Carbon dioxide is certainly present, but it's a supporting player, a secondary character in the grand celestial drama. 3I Atlas completely flips that script on its head. As astronomers analyzed its emissions, some measurements began to suggest something that seemed utterly backward. It appeared that a staggering 95% of the volatile emissions gushing from the comet might be carbon dioxide, with water relegated to being the minority component. That's not just a minor difference. It's a complete inversion of everything we see at home. It is like finding a world where the oceans are made of sand and the deserts are filled with water. Why on Earth, or rather, why in another star system, would a comet be so incredibly rich in carbon dioxide? One of the most compelling possibilities relates to the temperature at which it formed. In the swirling, chaotic disk of gas and dust that surrounds a newborn star, a protoplanetary disk, different materials condense from gas into solid ice at different distances from the star. Carbon dioxide ice can condense at higher temperatures, meaning it can form closer to its parent star than water ice can. What if 3I Atlas was born in a much warmer region of its home disk than our own comets were? It might have preferentially incorporated vast amounts of this warmer carbon dioxide ice while losing much of its potential water. Or perhaps the environment was different in other ways. Maybe its parent star had a different kind of radiation field, one that processed the ices in the disk in ways our sun doesn't. Or maybe the giant planets in that system, if it had any, migrated through the disk in a different pattern, violently stirring up the materials and mixing ingredients from different temperature zones in completely unexpected ways. The result would be a comet with a bizarre, hybrid composition unlike anything we could have predicted. Then there is the matter of the cyanide. Cyanide, or CN, is actually a very common molecule found in comets. It's one of the key ingredients that gives many comets their beautiful green color. But again, it's the asterisk behavior asterisk of the cyanide in 3I Atlas that is so strange. In our comets, cyanide and water tend to appear at around the same time, switching on together as the comet warms up because they have similar sublimation temperatures. But in 3I Atlas, the cyanide appeared much later in the warming sequence, long after the water had already started its impossible eruption. This delayed appearance suggests that the cyanide might be sequestered differently inside the comet. Maybe it's not frozen as a simple ice, but is instead trapped within more complex organic molecules that require extra energy and heat to break down and release their contents. Or perhaps it's frozen in distinct layers, buried deep beneath the primary water ice, only to be revealed after the top layers have boiled away. And of course, there is the ghost of a metal, that atomic nickel glowing green, completely separated from its usual partner, iron. We have already explored the mystery of this decoupled metal, but it is worth emphasizing again how it fits into this larger picture of a fundamentally alien chemistry. Every single element, every molecule we detect, is a clue. The volatiles, like water and carbon dioxide, tell us a story about the temperature and pressure conditions during the comet's formation. The refractory materials, like the minerals containing the nickel and iron, tell us about condensation sequences and the thermal processing of the disk. The ratio of gas to dust tells us about the comet's physical structure and how easily it breaks apart. Each piece of data is a pixel in a much larger image of its home system. Now, with all these ingredients laid out before us, water, complex organics, and cyanide, a key precursor in the chemistry that can lead to life, we have to confront the elephant in the room. We have to talk about the panspermia hypothesis. This is the grand and controversial idea that life itself, or at least its essential building blocks, can be spread through the vastness of space, hitching a ride on comets and asteroids. 3I Atlas, with its abundant water, its organic molecules, and its cyanide, seems to be carrying exactly the right ingredients you would pack if you wanted to design a celestial vehicle to seed a barren planet with the potential for life. But let's be very, very clear here. This is pure, tantalizing speculation. There is absolutely no evidence that 3I Atlas is carrying life. There is no evidence that any comet has ever carried life. The panspermia hypothesis is an incredibly intriguing idea, plausible in principle, but it remains completely unproven. And there are some very serious problems with it. The journey through interstellar space is brutal. For millions or billions of years, a comet is subjected to a relentless shower of high-energy cosmic radiation that tears apart complex molecules. The ultraviolet light from distant stars does the same. Fragile molecules like DNA and proteins, and even simpler building blocks like amino acids, would likely be destroyed. For any form of life to survive such an interstellar journey, it would need to be buried deep inside the comet, shielded by many meters of ice and rock. But what might survive are not living things, but chemical fossils. Complex molecules that were synthesized in the comet's parent system, perhaps in the atmosphere of a primordial planet, or on its surface could have been blasted into space and then incorporated into the comet as it formed. Those molecules, if they were stable enough and well protected, could survive the journey. And if we could ever get our hands on them and analyze them, they might tell us things we can't learn in any other way. They could reveal the atmospheric chemistry of an alien world. They might show us the ghostly remnants of metabolic pathways from a biosphere that has long since gone extinct. They might be messages written not in radio signals, but in the universal language of carbon, nitrogen, and oxygen, just waiting for someone to come and decode them. This is the dream that drives some scientists to propose missions to intercept one of these interstellar visitors. Not just to watch it from afar, but to send a spacecraft to match its incredible velocity, to land on its surface, to drill into its core, and to scoop up a physical sample for analysis. The technological challenges are immense. These objects are moving at tens of kilometers per second. Catching one would be one of the most difficult feats of engineering humanity has ever attempted. But the scientific payoff would be incalculable. A physical sample from another star system. Chemistry from a different corner of the galaxy. It would be the chance to find answers to questions we have barely learned how to ask. 3. I Atlas is already billions of kilometers away, hurtling back toward the darkness. We didn't catch this one. But it has shown us what's possible. It has given us a glimpse of what's out there, and it has made us profoundly hungry for more. The message in the cosmic bottle that is 3I Atlas, with its alien chemistry and ancient origins, forces us to confront the biggest questions we can ask about our place in the universe. It's a mystery that feels almost perfectly designed, a puzzle delivered to our doorstep from across the stars. But this raises another more grounded question. In an age where our telescopes are drinking from a fire hose of cosmic data, generating more information in a single night than was collected in the entire history of astronomy, how do we even spot these needles in the haystack? How do we find the one strange comet, the one bizarre star, the one signal that doesn't fit? We often imagine discovery as a singular moment of genius, a lone astronomer peering through an eyepiece, a sudden eureka, echoing through a domed observatory. But sometimes the most profound discoveries happen in a very different way. Sometimes they happen not because of a complex algorithm or a machine learning network, but because of the one tool that remains unsurpassed at recognizing the truly unexpected, the human eye, guided by human intuition. And sometimes that eye doesn't belong to a professional astronomer at all. To understand this, we need to leave the comet for a moment and journey to a different part of the sky, to a mystery that is, if anything, even stranger. Let me tell you about things called odd radio circles, or ORCs. If you've never heard of them, you're in good company. In the grand timeline of astronomy, they are practically brand new, having only been discovered in 2019. ORCs are exactly what they sound like, and yet they are so much more. They are vast, ethereal, perfectly circular structures, visible only in the invisible wavelengths of radio light. You could point the most powerful optical telescope, like the Hubble or the James Webb Space Telescope, at the right patch of sky, and you would see absolutely nothing. It would be empty, black space. But when a radio telescope listens to that same patch, they appear. Colossal rings of faint radio emission, sometimes hundreds of thousands of light years across, floating in the intergalactic void like cosmic smoke rings. And the most humbling part? Nobody knows for sure what they are. The leading theories suggest they could be the expanding shockwaves from cataclysmic events, like the collision of supermassive black holes, or perhaps the ghostly remnants of powerful winds blowing out from the centers of distant galaxies. But honestly, we are still just beginning to figure it out. They are a genuine grade a cosmic mystery. Finding them is incredibly difficult. They are exquisitely faint, easily lost in the crackling background static of the universe that our radio telescopes pick up. The automated detection algorithms that astronomers rely on to sift through their data tend to miss them entirely. Why? because those algorithms are trained to find what we expect to find: bright, compact point sources like stars, or well-defined, clumpy objects like galaxies. They aren't designed to recognize enormous, faint, perfectly circular ghosts. They are designed to find the signal, not the whisper. And this is where our story takes a turn, from the high-tech world of professional astronomy to the collective power of human curiosity. Enter a project called Radio at Home. This is a citizen science initiative where thousands of volunteers from all walks of life, teachers, artists, truck drivers, retirees, log onto their computers and visually inspect radio maps of the sky. They aren't given complex instructions. They aren't asked to look for anything specific. Their mission is much simpler and much more profound. They are simply asked to look for weird. And in March of 2025, a volunteer, someone just like you or me, flagged something that was beyond weird. Another volunteer found a gigantic radio galaxy with a peculiar, unexplained ring structure around it. Another discovered a faint ring at the very end of a galactic jet, a feature that our theoretical models had never even predicted could exist. These are discoveries that would have been completely lost, washed away in the digital flood, if humans hadn't been looking. There is a powerful lesson here that extends far beyond radio astronomy, a lesson that is deeply relevant to our mysterious comet, 3I Atlas. We are now entering an era of data deluge. The Vera Rubin Observatory, soon to come online in Chile, will generate 15 terabytes of data every single night. That's more data than is contained in the entire Library of Congress every 24 hours for 10 years. No human team can possibly look at all of that. No single set of algorithms can ever be programmed to catch every possible anomaly. We need both. We need the tireless efficiency of machines to handle the bulk processing, and we need the brilliant, quirky intuition of the human mind to catch the weird edge cases, the things that don't fit into any existing template. So let's bring this back to our comet. Could a citizen scientist have been the one to flag its anomalies early? Could someone, looking at the publicly available spectral data, have been the one to notice the strange signature of nickel without iron before the professionals did? Could a dedicated amateur, monitoring the comet's brightness night after night, have been the one to say, "Wait a minute, why is this thing getting so bright, so fast, so far from the sun?" Maybe, maybe not. But the point is that mysteries like 3I Atlas benefit from having as many eyes as possible on the data. Professional astronomers have the expertise, the training, the deep context, but they also have expectations. They have models they are trying to confirm, and they have incredibly limited time. Amateurs and citizen scientists come to the data with fresh eyes. They are not constrained by what is supposed to happen. They are free to see what is actually happening. A history of astronomy is filled with these stories. People with a passion and access to data, making discoveries that change our view of the cosmos. In the future, as our telescopes flood us with petabytes of information, these volunteers might just become our first responders to cosmic oddities. They might be the ones who raise the first alarm for the next interstellar comet, the next weird radio structure, the next thing that simply doesn't make sense. And when they do, the professionals will follow up, they will investigate, and they will figure out the physics. It's a partnership. And like all good partnerships, it is infinitely stronger than either component could ever be alone. The story of the citizen scientist who spotted the ghostly, intersecting radio rings is a beautiful testament to the power of human curiosity. It paints a romantic picture of a perfect partnership, the tireless machines collecting data, the passionate crowd sifting through it for anomalies, and the professional scientists providing the final analysis. It's a vision of a democratized science, where anyone with a computer and a keen eye can contribute to our understanding of the cosmos. But let's not pretend this is all sunshine and effortless collaboration. Behind this inspiring vision, there is a tension. It's a real, palpable tension that exists at the very heart of modern discovery. Because opening the gates of the scientific cathedral to the public means more than just welcoming new discoveries. It also means dealing with a flood of false positives, with well-meaning amateurs who flag things that turn out to be nothing more than instrumental artifacts or random noise. It means grappling with conspiracy theorists who see alien signals hiding in every single data glitch. And for professional astronomers, whose time is one of the most precious resources in all of science, this presents a genuine and understandable concern. This very debate has been held in the hallowed halls of institutions like the Royal Astronomical Society. On one hand, the benefits of citizen science are undeniable. It dramatically reduces the backlog of unanalyzed data. It allows massive projects to process far more information than would otherwise be humanly possible. And perhaps most importantly, it engages the public in the act of discovery, creating a powerful sense of shared ownership and enthusiasm for science. But on the other hand, the gatekeepers of science have a responsibility to maintain rigorous standards. Quality control is absolutely essential. A discovery isn't truly a discovery until it has been verified, cross-checked against other observations, and subjected to the grueling process of peer review. And all of that takes an immense amount of time and expertise. The problem of false positives is a very real one. Imagine an astronomer receiving an alert from a citizen science project about a potentially unusual object. They might spend days or even weeks of their limited telescope time and analytical resources following up on that candidate, only to eventually determine that the discovery was actually the glint of sunlight off a passing satellite, a cosmic ray hitting the detector in a weird way, or a simple flaw in the instrumental calibration. That is time that could have been spent investigating a genuine cosmic mystery. And when these false positives begin to pile up, a kind of cry-wolf effect can set in. Astronomers can become skeptical of all reports from citizen projects. The signal-to-noise ratio drops, and a sense of fatigue and frustration begins to build. Then there is the powerful and insidious effect of confirmation bias. This is the universal human tendency to see what we want to see. When people are looking for something specific, say, an alien megastructure, they have a tendency to find evidence for it, even when it's not really there. This happens to professional scientists too, of course, but the rigorous training and the adversarial nature of peer review provide powerful checks against it. Amateurs, who may lack that formal training, might not have those same checks and balances. They might see a fleeting pattern in a sea of random data and, through sheer enthusiasm, convince themselves that it's real. This is precisely how you get sensational claims about alien civilizations building structures around objects like Tabby's star or hidden messages being found in the precise timing of pulsars. Another significant hurdle is the understanding of calibration and error margins. Professional astronomers are trained to think statistically. They know how to assess the uncertainty in a measurement. They know the crucial difference between a signal that is statistically significant, meaning it is highly unlikely to be a random fluctuation, and one that is just a 1 sigma blip, a meaningless statistical ghost. An amateur might not have that nuanced understanding. They might report a detection that is, in the grand statistical scheme of things, completely meaningless. And finally, there is the simple, practical problem of bandwidth. If a citizen science project becomes too popular, if too many people start flagging too many things, the professional astronomers tasked with the follow-up can become completely overwhelmed. They can't possibly investigate every single candidate. They have to prioritize. And that means some genuine, incredible discoveries might get missed, simply because they are buried in an avalanche of well-intentioned, but ultimately incorrect reports. But here is the crucial thing to understand. These problems are not insurmountable. They are challenges, not deal breakers. And the scientific community is actively working to solve them. Smart systems can be put in place. Rigorous training protocols can help teach citizen scientists how to assess data quality, how to recognize common artifacts, and how to perform basic statistical checks. When volunteers are given the right tools, the false positive rate plummets. Mentorship programs, where experienced and trusted amateurs guide newcomers, can help maintain high standards of quality. Tiered validation systems can be incredibly effective. Imagine a system where a potential discovery has to be flagged independently by multiple, unrelated volunteers before it is ever elevated to the professional astronomers for a follow-up. That simple step can filter out the vast majority of spurious detections. And when these systems are in place, the opportunities that citizen science unlocks are simply enormous. Crowdsourcing the hunt for anomalies means you can search larger datasets more thoroughly than ever before. Having many independent eyes cross-checking the same data dramatically reduces the chance that a real anomaly gets missed just because one person happened to be having an off day. And bringing in diverse perspectives means that people from different backgrounds, who think in different ways, might notice subtle patterns that specialists, who are trained to look for specific things, might overlook. So let's bring this back, once again, to our mysterious comet 3I Atlas. Could a citizen astronomer have been the one to flag its bizarre nickel anomaly early? In theory, yes. The spectral data from our best telescopes is often made public. Anyone with the right software could download it and look for themselves. But in practice, spectroscopy is hard. It requires a deep understanding of atomic line identifications, wavelength calibrations, and signal-to-noise assessments. It's not something you can just do casually. But maybe, with the right training, with the right guidance, with a dedicated community of amateurs working together, someone could have noticed that strange, lonely nickel signature before it ever made the headlines. The same goes for its impossible water production. The light curves of comets, the precise measurements of their brightness over time, are often built from data contributed by a global network of amateur astronomers. If those amateurs had also been looking at the publicly available ultraviolet data from the Swift telescope, and if they'd been trained to recognize unusual patterns of activity, they might have been the first to flag the superlinear brightening of 3I Atlas. They might have been the ones to sound the alarm and say, "This doesn't look like a normal comet," long before the professional surveys confirmed it. The evidence that this partnership works is all around us. The hunt for exoplanets has been revolutionized by citizen scientists analyzing data from the Kepler Space Telescope. Projects like Planet Hunters have allowed volunteers to discover multiple confirmed alien worlds that the algorithms had missed. Amateur asteroid hunters have found near-Earth objects that the professional surveys overlooked. Amateur nova hunters regularly beat the professionals to the discovery of exploding stars because they are out there, looking every single night with their own small telescopes, while the big professional telescopes are scheduled months or even years in advance. The conclusion here is not that we should replace professional astronomers with amateurs. That's absurd. The conclusion is that we need both. We need the deep expertise, the theoretical frameworks, and the rigorous validation that only professionals can provide. And we need the sheer breadth of coverage, the fresh perspectives, and the passionate, tireless number of eyes that only the citizen science community can offer. It is not a competition. It is a necessary partnership. And in this new era of data deluge, it is the only way we will be able to make sense of the flood of mysteries the universe is sending our way. The partnership between professional and citizen scientists, as complex as it may be, represents our collective, rational attempt to understand the universe. It is a structured effort to sift through the noise and find the genuine mysteries, the real clues like those offered by 3I Atlas. But our relationship with the cosmos isn't always so rational. There is another, more primal way that we interact with the night sky, a way that is driven not by data and logic, but by a deep, ancient, and often misleading instinct. We are pattern-seeking creatures, and sometimes we find patterns that are nothing more than ghosts in our own minds. As the mystery of 3I Atlas deepened, Another celestial story was unfolding, completely unrelated, yet destined to become entangled with it. The autumn skies of October 2025 brought an unusual and beautiful treat for skywatchers. Two notable celestial bodies, Mercury and Ceres, put on a spectacular show. Mercury, the elusive innermost planet, swung into a particularly favorable evening apparition, appearing bright and unusually high above the horizon just after sunset. At the same time, Ceres, the largest object in the asteroid belt and a dwarf planet in its own right, reached opposition. This is the point in its orbit where it is directly opposite the sun in our sky, making it shine at its brightest and appear at its closest to Earth. For amateur astronomers, it was a wonderful coincidence, a perfect opportunity to view two fascinating and often difficult to spot objects. But on the vast, chaotic, and interconnected web of social media, people started doing what people do best. They started connecting the dots. Suddenly, a narrative began to emerge. Mercury is clearly visible. Ceres is at its brightest. And now, this bizarre interstellar comet, 3I Atlas, is out there, acting alive, spewing water and glowing green. The question began to bubble up in forums and on comment threads. Were these events related? Was there some kind of cosmic alignment taking place? Were the combined gravitational fields of the solar system somehow amplified by this configuration, triggering or enhancing the comet's impossible activity? Let's be absolutely clear, right from the start. The scientific answer to that question is a firm, unequivocal no. There is no connection whatsoever. The orbit of Mercury, a tiny planet hugging close to the sun, has absolutely nothing to do with the outgassing of an interstellar comet billions of kilometers away. The position of Ceres relative to the Earth has no physical influence on the complex chemistry happening on the surface of that distant, icy rock. These are completely independent astronomical events, beautiful coincidences of celestial mechanics that just happen to be visible at the same time. Nothing more. But that simple, rational explanation is often no match for the power of human psychology. We are wired to find patterns. It is one of our most fundamental survival traits. Our ancient ancestors, who noticed that certain red berries always grew near a source of clean water, or that the tracks of a certain animal often led to its den, were far more likely to survive and pass on their genes than those who saw the world as a series of random disconnected events. Our brains evolved to be hypersensitive to patterns, to the point where we often find them even where they don't actually exist. This is a phenomenon as pareidolia, but on a cosmic scale. Pareidolia is what makes us see a face in the clouds, a man in the moon, or hear ghostly voices whispering in the static of a radio. It is our pattern detection engine gone into overdrive. And it happens with celestial events all the time. For millennia, ancient cultures saw powerful omens in the alignment of the planets. When a bright comet unexpectedly appeared in the sky during a great battle, it was interpreted as a sign that the gods were angry or that they had chosen a victor. When a group of planets gathered together in one small patch of the sky, it was thought to signal the birth or the death of kings. We may think we are beyond such ancient superstitions, but the instinct remains. The year 1910 provides a perfect and cautionary historical analogy. That was the year that Halley's comet returned, swinging through the inner solar system on its famous 76-year orbit. And people were utterly terrified. Astronomers, using the new tool of spectroscopy, had detected a toxic gas called cyanogen in the comet's tail, the very same molecule that gives 3I Atlas its green glow. The newspapers of the day, hungry for a sensational story, ran with it. Headlines screamed, "Comet's poisonous tail will pass over Earth." Panic ensued. People rushed out to buy gas masks. Some sealed their windows and doors with tape, convinced the air would become toxic. There were even tragic reports of suicides by people who were genuinely convinced that the comet was coming to kill them. Of course, nothing happened. The tail of a comet is an incredibly diffuse thing. It is, by terrestrial standards, a hard vacuum. The actual amount of cyanogen that reached the Earth's atmosphere was negligible, completely undetectable. The comet posed no threat at all. But the mere coincidence of the comet's spectacular appearance with other, completely unrelated events, a spike in solar activity, political unrest in Europe, a series of earthquakes fueled the panic. People connected dots that simply did not connect. We are seeing the exact same psychological mechanism at play now with 3I Atlas. The comet is genuinely weird, a true scientific anomaly. Mercury and Ceres just happen to be putting on a good show at the same time. And suddenly, people are constructing elaborate narratives. Maybe the comet is being awakened by some kind of solar system resonance. Maybe its trajectory is being subtly and deliberately altered by gravitational perturbations we don't understand. Maybe this is all part of a larger, hidden pattern. The astronomers, of course, have run the numbers. The gravitational influence of a tiny planet like Mercury on an object in the outer solar system is for all practical purposes 0. Ceres is even smaller and even less influential. In fact, the combined gravitational pull of every single planet in our solar system, all pulling together, could not significantly alter the behavior of 3I Atlas at the vast distances we are observing it. The comet is doing what it's doing because of its own unique internal processes, the gentle heating from solar radiation and its own alien composition. It has nothing to do with where Mercury happens to be in its orbit. But facts don't always matter when a narrative is compelling. The human brain craves stories. We want events to be connected, because a universe of disconnected, random events feels chaotic and meaningless. If the comet's activity is somehow linked to the positions of the planets, then there is a sense of order, of predictability. There is a hidden meaning. If the events are unrelated, then we are simply living in a universe where strange things just happen sometimes. And for many, that is a psychologically uncomfortable thought. Confirmation bias then acts as a powerful amplifier for this effect. Once you start looking for connections, you will find them everywhere. You might remember that Mercury was also visible during a previous comet discovery, or that Ceres was near opposition when another unusual object was detected. You conveniently forget to consider the hundreds of times when Mercury was visible and nothing happened, or the dozens of other unusual objects that were found when Ceres was nowhere in sight. The brain filters out all the non-coincidences and remembers only the ones that perfectly fit the emerging narrative. And in our modern world, social media amplifies this exponentially. In the old days, if you had a fringe theory about planetary alignments affecting comets, you might tell a few of your friends who would probably tell you it was nonsense, and that would likely be the end of it. Now, you can post that theory online and instantly find a global community of people who think the exact same way. You can share links, images, and crudely drawn charts showing the alignments. Someone else adds a new, unrelated piece of evidence. Someone else shares it even further. Before long, you have a full-blown alternative narrative that is actively competing with the scientific explanation. The lesson here is not that people are stupid or gullible. The lesson is that coincidences are powerful, and our brains are not well calibrated to dismiss them. Statistically, with thousands of astronomical events happening all the time, some of them are bound to coincide purely by chance. And those coincidences will feel profoundly meaningful, even when they are not. This matters because it directly affects how people interpret a genuine anomaly like 3I Atlas. If you are already primed to see cosmic conspiracies, to believe that hidden alignments matter, then the comet's weird behavior is no longer just a scientific puzzle. It becomes evidence of something much larger, much stranger, and perhaps much more sinister. The human mind's tendency to weave narratives from coincidence, to see patterns in the celestial dance, is a powerful force. It can transform a random alignment of planets into an omen, and a scientifically fascinating comet into a piece of a grand conspiracy. This instinct to question the official story, to look for the hidden truth, is not just confined to the distant cosmos. It thrives right here on Earth, especially when it comes to one of humanity's most audacious endeavors, sending people into space. If a comet's strange behavior can fuel speculation, what happens when the anomaly isn't a distant rock, but a human spaceflight that feels off? What happens when the machinery of storytelling itself seems to break down? This brings us to an even stranger chapter in this whole saga. A story not of cosmic anomalies, but of a deeply human one. A ghost not in the stars, but in the media machine. Let's travel to the Texas desert, to the events of October 8th, 2025. On that day, Blue Origin's New Shepard rocket was scheduled for its next mission, S-36. The flight profile was familiar, almost routine by now. 6 passengers would be carried to the edge of space, cross the internationally recognized Kármán line, experience a few life-changing minutes of microgravity, and then descend gracefully under parachutes for a soft landing. It was slated to be the company's 15th crewed mission, another successful notch in its growing space tourism program. And, according to all official accounts, that is exactly what happened. The rocket launched, the capsule separated, the passengers floated, the parachutes deployed, the capsule touched down. Success. But there was a strange detail. One of the 6 passengers was a mystery flyer, their name kept secret from the public until after the mission was complete. The official story was simple. ABC News covered it briefly. The online publication Medium ran a short piece. A handful of dedicated space journalists tweeted about the successful landing. The mystery passenger was revealed post-flight as a private individual who had simply requested anonymity during the flight itself. A perfectly reasonable request for someone paying a large sum for a private experience. Nothing unusual there. But here is where it gets strange. Here is what started to nag at anyone who follows the space industry closely. It was the silence. An eerie, almost suffocating lack of coverage. In an age of information overload, this multi-million-dollar spaceflight, carrying 6 human beings off the planet, barely registered a blip. Think about that for a moment. Just a few short years ago, an event like this would have been headline news around the world for days. There would have been viral videos of the passengers' reactions, trending hashtags, celebrity commentary, endless memes, and detailed breakdowns on TikTok and YouTube. But for NS-36, there was almost nothing. Social media shrugged and moved on within hours. The story simply vanished, like smoke in the wind. Why? Why was there so little documentation? Blue Origin usually releases stunning, high-definition footage from inside the cabin, beautiful shots of the passengers floating, laughing, their faces pressed in wonder against the enormous windows. Where were those images? Why weren't they splashed across every news site and social media platform? Why did the reveal of the mystery passenger generate almost zero curiosity? Who were they? Why did they want to remain anonymous for the flight? These are the natural, obvious questions that usually fuel days of public speculation and interest. Instead, there was just radio silence. It was as if the flight had happened in a complete vacuum. Not just the vacuum of space, but a vacuum of public attention. And when there is a vacuum, a void where a story should be, that absence starts to feel like its own kind of presence. The silence itself becomes louder than any press release ever could be. And in that silence, you start to wonder. You start to ask uncomfortable, paranoid questions. Did this flight really happen exactly as it was described? Were there really 6 passengers? Or was the manifest somehow different? Was the mystery passenger a real person, or just a convenient narrative device to explain the unusual lack of pre-flight publicity? Did the capsule actually launch on October 8th, or was footage from a previous, well-documented flight simply repackaged with a new date stamp? These are the thoughts of a conspiracy theorist, the kind of reasoning that sees shadows lurking in every corner and trusts nothing. But sometimes, just sometimes, the absence of evidence feels like evidence of absence. When something that should make a loud noise is completely silent, you have to ask why. Now, let's contrast this deafening silence with the events of just 6 months earlier, in April 2025. Blue Origin launched another New Shepard mission, and that one exploded into the public consciousness. Not because of a malfunction, but because of who was on board. It was a high-profile, all-female crew featuring celebrities like Katy Perry and Gayle King. It was a flight perfectly designed to generate headlines. And it did, but not the headlines Blue Origin had hoped for. Within hours of the live stream ending, social media erupted with a firestorm of conspiracy theories. People claimed the entire flight was faked. They became amateur forensic analysts, dissecting every single frame of the footage, looking for inconsistencies. The behavior of the passenger's hair in zero gravity became a bizarre digital battlefield. Does it float correctly? Is it moving too stiffly? Is that real hair, or a wig, or a computer-generated image? The capsule's hatch became another focal point. Someone claimed it opened differently than it had in previous flights. They posted side-by-side comparison photos, drew red arrows, and circled supposedly anomalous details. Wasn't the latch on the other side last time? Didn't the door swing outward before? Why does this look different? Then came the really wild stuff, claims of green screens, allegations that the passengers were filmed in a studio, with fake windows showing pre-recorded footage of the Earth, accusations that their hands looked like mannequin hands, too smooth, too plastic, complaints about the absence of visible scorch marks on the capsule after re-entry. Every tiny, insignificant detail was twisted into proof of a massive deception. Professional journalists and space experts methodically debunked the claims, one by one. Hair behaves weirdly in microgravity. It responds to air currents and static electricity in ways we're not used to seeing. The hatch mechanism was identical across all flights. Different camera angles and lighting can create optical illusions. Reflections in the astronauts' visors can distort perspective. Scorch marks aren't always visible, depending on how much dust kicks up at the landing site and the resolution of the camera. But the debunking didn't stop the theories. If anything, it fueled them. The people who wanted to believe the flight was a fake simply interpreted the debunking as part of a massive cover-up. They dug even deeper, found more evidence, and built ever more elaborate models of how the hoax had been perpetrated. The conspiracy became a self-sustaining ecosystem of belief. So now we are left with 2 flights from the same company, using the same rocket, with the same basic mission profile, just 6 months apart. One generated a furious firestorm of public attention and paranoid doubt. The other barely made a sound. And you have to ask yourself, which one is actually more suspicious? The loud, messy, controversial event that everyone is talking about, or the quiet, clean, perfectly packaged event that no one seems to have noticed at all? We have journeyed from a mysterious comet screaming water into the void, to the citizen scientists who hunt for ghosts in radio static, and finally to the strange silence surrounding a human spaceflight. Each of these stories, in its own way, is about a kind of anomaly, a deviation from the expected, a signal that doesn't fit the pattern. And it seems that the universe, in its infinite complexity, just keeps throwing us these curveballs. It presents us with objects that don't fit our models, signals that make no logical sense, and phenomena that seem to violate our carefully constructed rules. And every single time this happens, without fail, we as a species do 2 very predictable things. First, we scramble to understand the science. We point our telescopes, we crunch the numbers, we propose hypotheses, and we engage in the rigorous logical process of discovery. But second, and just as powerfully, we project ourselves onto the mystery. The anomaly becomes more than just a data point. It becomes a mirror reflecting our deepest hopes, our most profound fears, and our eternal questions about our place in the cosmos. Think back to Oumuamua, our very first confirmed interstellar visitor, which tumbled through our solar system back in 2017. It was a complete enigma. It was reddish, strangely elongated, and it was accelerating. Not by much, but by a measurable amount as it left the solar system, a subtle push that could not be explained by gravity alone. It was as if something was gently stepping on its gas pedal. The scientific community went into overdrive trying to explain it. Maybe it was outgassing, they proposed. Even though no gas was directly detected, perhaps it was releasing small, invisible amounts of volatiles that created a tiny rocket-like thrust. Or maybe, another theory suggested, it was a bizarre hydrogen iceberg, a solid chunk of frozen hydrogen that would sublimate invisibly in the faint warmth of the sun. Or perhaps it was a nitrogen iceberg, a fragment ripped from the surface of a Pluto-like exoplanet. But a small subset of people, including some very credible scientists, proposed something far more radical. What if Oumuamua was artificial? What if that gentle push was from something like a light sail, a vast, thin sheet of material being pushed by the pressure of sunlight itself? That would perfectly explain the acceleration without any need for gas. And if it was artificial, then maybe it was a probe from another civilization. Maybe it was actively exploring. Or perhaps it was derelict, a ghostly piece of alien space junk from a long-dead society, tumbling silently through the ages. The exact same thing happened with Tabby's star, a celestial object with the catalog number CT8,462,852, was a completely ordinary-looking star in the Kepler Space Telescope's field, a view that was exhibiting the most bizarre dimming patterns ever seen. It would experience deep, irregular dips in its brightness, sometimes dropping by a staggering 20% or more. No planet could do that. No known planet is nearly large enough to block that much light from its star. And the dips didn't repeat with any predictable regularity, as a planet's transit would. Astronomers, once again, proposed a whole host of natural explanations. Perhaps it was a massive swarm of comets, a dusty cloud of debris from a recent planetary collision, or even strange fluctuations within the star itself. But one scientific paper, half-jokingly at first, suggested another possibility. What if we were seeing an alien megastructure? A Dyson swarm, a vast collection of solar panels or orbiting habitats that an advanced civilization had built around its star to collect its energy. Such a structure would, in theory, block the starlight irregularly as its different components moved across our line of sight. It fit the data, sort of. And in that moment, a star became a global sensation. Odd radio circles, fast radio bursts, and now, 3-eye Atlas. Every single mystery becomes a blank screen onto which we project our own narratives, our own existential dramas. Are we alone in the universe? Is the cosmos a place of cold, indifferent physics, or is there some intention behind it? Are there others out there? And if they do exist, are they benevolent explorers like us, or are they incomprehensibly alien? The psychology at play here is incredibly powerful. Pareidolia, that instinct to see patterns and randomness, is a huge part of it. We see faces in the clouds, we hear voices in white noise, and we are primed to see intelligence in astronomical anomalies. This isn't a sign of foolishness. It's a deep and fundamental feature of the way our brains work. We are pattern recognition engines, and we are deliberately biased toward false positives. From an evolutionary perspective, it was always better for our ancestors to mistake a shadow for a predator than to mistake a real predator for a shadow. But there is also a deeper, more existential longing at work. Many of us want there to be contact. We want to know that we are not the only sparks of consciousness in this vast, cold, and seemingly empty universe. Every unexplained anomaly represents a chance, a tiny possibility, a door that might just open onto something truly extraordinary. And so we push on those doors, and we push on them hard. 3-eye Atlas is the perfect mirror for our time. In its ethereal, glowing green coma, we can see our own curiosity reflected back at us. We see our insatiable hunger for meaning, our desperate hope that the universe is not just stranger than we imagine, but stranger than we can imagine. And maybe it is. Maybe one day we will find something genuinely, undeniably inexplicable. Something that forces us to rewrite the laws of physics, or to finally accept that we are not alone. But that day has not come yet. For now, what we have is a comet. A weird comet, a fascinating comet, a comet that is challenging our models and pushing the boundaries of our knowledge. But still, in all likelihood, just a comet. And perhaps that in itself is enough. Because even the natural mysteries, the puzzles that the universe sets for us without any need for alien intervention, are absolutely extraordinary. The fact that a piece of another solar system, potentially billions of years older than our own, can travel across the galaxy and end up in our backyard, carrying with it a chemical story we've never read before, is a wonder of the highest order. We don't need aliens for the universe to be awe-inspiring. We just need to keep looking up. The mirror of mystery, reflecting our own hopes and fears, is a powerful metaphor for how we engage with the unknown. But if we can set aside our projections for a moment and look at these visitors with the clear eyes of science, we see that they are something else entirely. They are more than just puzzles or screens for our imagination. They are artifacts. They are emissaries. Imagine the galaxy not as a vast, empty space, but as a library. An ancient, sprawling library filled not with books, but with objects. Every comet, every asteroid, every rogue planet that is violently ejected from its home during the chaotic formation of a planetary system is flung out into the galactic commons. Each one of these objects is a message in a bottle, a time capsule carrying incredibly detailed information about the star system where it was born. And every now and then, purely by chance, one of those bottles washes up on our celestial shore. That is what interstellar objects truly are. They are postcards from alien systems. Not necessarily alien in the sense of extraterrestrial intelligence, but alien in the truest sense of the word. Foreign, different, formed under a unique set of conditions that were unlike those that shaped our own solar system. Every single one we detect is a precious data point, a single sample in a vast cosmic survey. And with enough of these samples, we can begin to piece together the grand, diverse story of how planetary systems are built across our entire galaxy. Our own solar system's comets, as fascinating as they are, can only tell us so much. They are all, in a sense, related. They all formed from the same primordial, well-mixed cloud of gas and dust under the influence of the same young sun. They certainly have variations, of course. Some are richer in carbon monoxide, others are richer in water, depending on where in that protoplanetary disk they formed and what temperatures they experienced over their long history. But ultimately, they are family. They are siblings, or at best, distant cousins. They all speak the same fundamental chemical language. Interstellar comets, on the other hand, are complete strangers. They were born elsewhere, orbiting different types of stars, in disks with completely different chemical compositions, different temperature gradients, and different chaotic, dynamical histories. And so far, every single one we have had the privilege of meeting has been profoundly, uniquely different. Oumuamua was our first. It was dry, refusing to outgas, with a strange, elongated shape, and it was accelerating in a way that still defies a simple explanation. It didn't look like our comets. It didn't act like our comets. If it even was a comet, it was a type we had never before encountered. Then came 2I Borisov. This one was much more familiar. It was rich in carbon monoxide and exhibited fairly typical comet-like behavior. But even it was subtly off. Its gas-to-dust ratio suggested it had formed in a much colder environment than most of our own comets. It was like hearing a dialect of a language you speak. You can understand it, but the accent is noticeably different. And now we have 3I Atlas, water and carbon dioxide gushing at impossible distances. Nickel appearing without its faithful partner, iron, cyanide showing up late to the party. Nothing about its behavior fits neatly into our existing experience. It is speaking a chemical language that we are only just beginning to recognize, let alone understand. 3 objects, 3 wildly different chemistries, 3 completely unique stories. If we dare to extrapolate from this tiny sample size, if we assume that these first 3 visitors are in any way representative of the broader galactic population, then the diversity of cometary compositions throughout our galaxy must be absolutely staggering. It implies that not all planetary systems produce comets like ours. In fact, it might be that most of them don't. Think for a moment about what that really means for the chemistry of the cosmos. In some star systems, the comets might be dominated not by water ice, but by nitrogen ice, like the frozen surface of Pluto. In others, perhaps methane is the primary volatile, creating comets that behave in completely different ways as they warm. In systems that form around much more massive, hotter stars, this snow line, the critical distance from the star where water ice can condense, is pushed much farther out. The comets in those systems would form in much colder regions and would likely carry a very different mix of volatile ices. In systems where giant planets migrate dramatically through the disk, they would act like colossal cosmic blenders, stirring up all the materials and mixing ingredients from different temperature zones, creating comets with bizarre hybrid compositions that we can barely imagine. Could some of these comets be carrying molecules that we have never even seen before? Molecules that are thermodynamically possible, but require unique chemical formation pathways that simply don't exist in our own solar system? Exotic organic compounds, strange crystalline forms of ice, compounds that would make a chemist's eyes light up with excitement. The answer is almost certainly yes. The universe is an immense place. The parameter space of stellar masses, disk compositions, radiation fields, and dynamical environments is enormous. Nature, through billions of years and billions of star systems, has had ample opportunity to explore that entire parameter space. Some of the results simply have to be strange. Now, let's take this idea one critical step further. If we believe that life as we know, it requires certain essential chemical building blocks, liquid water, a suite of organic molecules, elements like phosphorus, nitrogen, and sulfur, then the composition of these cometary delivery trucks matters profoundly. A comet that lacks these key ingredients is, for all intents and purposes, sterile. It cannot seed a young planet with the potential for life. Maybe many, or even most, interstellar comets are sterile. Maybe Oumuamua was nothing more than a lifeless rocky brick tumbling through the void. But if even a tiny fraction of these comets carry the right chemistry, that fraction is incredibly important. Because comets are the galaxy's great wanderers. They travel between the stars. They cross light years of empty space. And if they are indeed carrying complex organic molecules, amino acids, maybe even dormant microbes shielded deep within their icy hearts, then the building blocks of life itself can spread across the entire galaxy. This is the heart of the panspermia hypothesis. It is controversial. It is unproven. But it is not impossible. And 3I Atlas, with its abundant water, its organics, and its cyanide, has all the right ingredients. It's probably not carrying life itself, but it is carrying the very chemistry that could, if delivered to the right kind of planet, lead to life. Every new interstellar object we detect expands our sample size. Right now, we have 3. In 10 years, with new observatories like the Vera Rubin Observatory coming online, we might have dozens. In 50 years, perhaps hundreds. And with each one, we will measure its composition, trace its trajectory, and analyze its activity patterns. We will begin to build a true statistical understanding of what's out there in the galactic library. Maybe we will find that water-rich comets, like our own, are actually quite common. Or maybe we will find that our solar system is the real oddball, and that most systems produce dry, carbon-rich bodies. Either answer would be a fascinating revelation. And maybe, just maybe, one day we will find a comet with a clear and unambiguous biomarker molecules that are incredibly difficult to explain without biology. That would be the discovery of a lifetime. That would tell us once and for all that life arose elsewhere, and that biochemistry is not a miracle unique to Earth. We haven't found that yet. 3I Atlas is not carrying life, as far as we can tell. But it is carrying information. And in the grand library of the cosmos, information is the most precious currency of all. The galactic library, with its countless messages and models, offers us a breathtaking vision of cosmic diversity. Each interstellar visitor is a new book, a new story of a different world. But to truly read these stories, we have to learn to decipher the language in which they are written. And that language is chemistry. We have to zoom in from the grand narrative to the finest of details, because sometimes the most profound secrets are hidden in a single anomalous fingerprint. So let's return to that strange, lonely nickel, the ghost of a metal glowing green in the coma of 3I Atlas. It's not just a scientific curiosity. It's a clue of the highest order. It's a chemical fingerprint, and just like a fingerprint left at a crime scene, it can tell you an incredible amount about where someone has been and what they've been through. To understand its significance, we have to think about stars. Stars are the great factories of the universe. Deep within their cores, the unimaginable pressures and temperatures of nuclear fusion take the simplest elements, hydrogen and helium, and forge them into the heavier elements that make up our world: carbon, nitrogen, oxygen, silicon, sulfur, and all the way up to iron. But the story doesn't end there. When the most massive stars reach the end of their lives, they don't just fade away. They explode in cataclysmic events called supernova. In the final violent moments of these explosions, even heavier elements are created, including the nickel and iron at the heart of our mystery. All of these newly forged elements are then blasted out into space, scattered across the galaxy like seeds. They mix with the vast clouds of interstellar gas, and over millions of years, are eventually incorporated into the next generation of stars and planets. And this is the crucial point, not all stars are born with the exact same recipe. The abundance of these heavy elements, what astronomers collectively call metallicity, varies across both space and time. Young stars, like our Sun, which formed relatively recently in the galaxy's history, are born from gas that has been enriched by many previous generations of supernova. They have a high metallicity. Old stars, on the other hand, which formed when the galaxy was much younger and fewer supernovae had occurred, have a much lower metallicity. They are made of more pristine, less processed material. The plot thickens even further when we consider the metals themselves. Nickel and iron are both produced in supernova, but the exact ratio between them can vary depending on the specific type of explosion. A type Ia supernova, which happens when a small dense star, called a white dwarf, accretes too much matter from a companion and explodes, produces a different nickel-to-iron ratio than a core collapse supernova, which is the death of a single truly massive star. Now, let's connect all of this back to our comet. We already have a tantalizing clue that 3I Atlas might have come from the thick disk, that ancient, puffed-up population of older stars. The stars in the thick disk generally have a lower overall metallicity, but the specific ratios between their different heavy elements can be quite varied. If the strange decoupling of nickel and iron that we are seeing in 3I Atlas is a direct reflection of the composition of its parent star, then that comet is no longer just a visitor. It becomes a tracer. It is telling us a detailed story about the specific processes of galactic chemical evolution in a way that we can't easily access otherwise. Because here is the thing, we can and do analyze the atmospheres of distant stars using spectroscopy. We can measure their iron, their nickel, their carbon, their everything. But stars are incredibly far away. We can only study a tiny fraction of them in such exquisite detail. And most importantly, we can't study the stars that no longer exist, the stars that lived and died billions of years ago, whose light has long since faded. But the comets born in those ancient systems are time capsules. They perfectly preserve the exact chemical conditions of their birth. If we could somehow get a physical sample of 3I Atlas, if we could analyze its isotopes, its trace elements, and its mineral structures in a lab here on Earth, we would be holding in our hands a physical piece of a star system that might be billions of years older than our own and thousands of light years away. We would be reading history written in the very language of atoms. Now, with that foundation laid, let's allow ourselves to entertain a much more speculative idea. It's a fringe idea, certainly, but one that gets quietly discussed in certain scientific circles when a truly inexplicable anomaly appears. Could a strange metal signature like this, a high concentration of one valuable metal without its usual partners, be a signature of something processed? Not processed by natural events like thermal metamorphism inside a planet, but processed technologically. If you imagine a highly advanced civilization, one that is capable of mining asteroids, refining metals on an industrial scale, and building vast structures in space, they would inevitably generate waste. They would produce slag, tailings, and industrial exhaust. And that material would, by its very nature, have highly unusual elemental ratios, because industrial processes are all about selection. You might extract iron for its structural properties and discard the nickel-rich residue. Or you might specifically use nickel for some advanced technological application and dump everything else. Now, imagine if a comet were to form in a debris disk that was, for some reason, contaminated with this industrial waste. It might inadvertently incorporate those anomalous metals into its icy body. And then, millions or billions of years later, that comet gets ejected from its home system, wanders the galaxy, and eventually arrives in our solar system. We detect the bizarre nickel anomaly and scratch our heads, trying to find a natural explanation that doesn't quite fit. To be absolutely, unequivocally clear, there is no evidence whatsoever that 3I Atlas is artificial or contaminated with alien technosignatures. None. The idea is speculative to the point of being pure science fiction. The vast majority of scientists would dismiss it outright, and for good reason. But it is not, strictly speaking, physically impossible. And in the face of a genuine mystery, like the nickel-iron decoupling, for which we still have no clear natural explanation, even the wildest of ideas deserve at least a fleeting moment of consideration. The far more likely explanation is still rooted in prosaic, if unfamiliar, chemistry. Perhaps it's the organometallic compounds, or some strange fractionation process during condensation. It's almost certainly a natural process that we just haven't thought of yet, one that might be common in other star systems, but happens to be rare or completely absent in ours. But here is what is so exciting about this. Every single comet carries its own unique chemical signature, a cosmic barcode written in elements and isotopes. If we can begin to build a library of those signatures, if we can catalog the detailed compositions of dozens or even hundreds of these interstellar visitors, we can start to map the chemical geography of our galaxy. We could begin to correlate chemical signatures with trajectories. A comet arriving from the direction of the dense, star-filled galactic center might have systematically different abundances than one arriving from the sparse, ancient outer halo. We could use these comets as tracers, as probes of galactic structure and evolution. Imagine a future where our detection technology is so good that we are cataloging these interstellar objects by the dozens every single year. Each one gets a detailed spectroscopic analysis. Each one's trajectory is traced back as far as possible. Each one's unique chemical composition is added to the growing database. Eventually, patterns would have to emerge. We might find that comets from one region of the galaxy are systematically carbon-rich, while those from another are water-rich, and we could start to understand why. 3i Atlas is just the beginning of that grand library. It is one entry, one single, baffling data point, but it is a start. And its strange, decoupled nickel is a powerful reminder that every single one of those data points has a story to tell. Every element ratio is a clue. And if we are patient enough, and if we are careful enough, we can learn to read those stories and, piece by piece, reconstruct the grand, sweeping history of the galaxy itself. The story of 3i Atlas, this single mysterious book from the Galactic Library, is a profound one. But the existence of just 3 confirmed interstellar visitors in the span of only 7 years, Oumuamua, 2i Borisov, and now 3i Atlas, tells us something even more profound. It tells us that these objects are not the once-in-a-lifetime rarities we once thought they were. They are common. The library is vast, and its books are constantly in motion. The fact that we have seen 3 so recently, with our current, still limited technology, is not just a lucky coincidence. It's a statistical clue. It's enough data for us to perform a kind of cosmic census, to estimate just how many more of these wanderers are out there, passing silently through our solar system, completely undetected, and the numbers are astonishing. Astronomers have run the complex calculations, factoring in the detection rates of our current surveys, their sky coverage, and the observed properties of these first 3 objects. Their best estimate is that at any given moment, there are probably several interstellar objects currently inside the orbit of Jupiter. Right now, as you are listening to this, they are small, they are dark, and they are moving incredibly fast, making them all but invisible to most of our telescopes. We've only managed to detect 3 because we got lucky. They happened to pass close enough to the Earth, or they happened to be bright enough, or they happened to cross a patch of sky where one of our powerful survey telescopes was looking at the exact right time. This raises a humbling question. How many do we miss? For every one interstellar comet we manage to spot, how many dozens, or even hundreds, pass through our solar system completely unnoticed? They arrive, they swing around the sun, and they depart, their precious cargo of information remaining forever unread. Detection is hard, but it is about to get a whole lot easier. We are standing on the precipice of a revolution in astronomy, an era where our ability to scan the sky is about to take a quantum leap forward. New surveys are coming online with unprecedented sensitivity and the ability to cover the entire sky with breathtaking speed. The undisputed titan of this new era is the Varro-Rubin Observatory, currently under construction on a mountaintop in Chile. When it sees first light, it will begin to scan the entire visible night sky every few nights, imaging everything down to incredibly faint magnitudes. It is a machine built to detect change. It will find anything that moves or varies in brightness, exploding supernova, hungry black holes, and, most importantly for our story, thousands of new comets and asteroids. And among them, it will find interstellar objects. The estimates of what the Rubin Observatory will achieve are staggering. Some scientists predict it could detect, on average, 1 new interstellar object every single month, maybe even more. That's a minimum of 12 per year. In just 1 decade of operation, we could go from our current paltry sample of 3 to a rich catalog of over 100 confirmed interstellar visitors. That is no longer just a collection of curiosities. That is a true statistical sample. That is enough data to start drawing real, meaningful conclusions about the compositions, origins, and populations of these objects across the galaxy. We could finally begin to answer the big questions. Are water-rich comets like ours common or rare? Do most comets carry the building blocks of life? Do different regions of the galaxy produce chemically different types of comets? The Square Kilometer Array, A colossal radio telescope network being built in Australia and South Africa will also be a key player. Its incredible sensitivity will allow it to detect the faint molecular emissions from comets, even very small or distant ones. The SKA could potentially spot interstellar comets that are too dark or too dusty for optical telescopes like Rubin to see. And powerful space-based observatories like the James Webb Space Telescope will contribute by studying these objects in the infrared and ultraviolet, catching comets that are active but whose light might be obscured at visible wavelengths. Every new instrument we build expands our detection capability, our ability to see these faint, fast-moving ghosts. But detecting these objects is one thing. Studying them in detail is another challenge entirely. Interstellar objects move with incredible speed, often tens of kilometers per second relative to our Sun. This means that by the time we spot one, calculate its trajectory, confirm that it's interstellar, and scramble to schedule follow-up observations with our most powerful telescopes, it's often already on its way out the door. Oumuamua was a classic case. We discovered it as it was already heading away from the Sun. We got one good, frantic look at it, and then it rapidly faded into the distance, becoming too faint for even our best telescopes to observe, its secrets forever lost to us. With 2I Borisov, we were luckier. We caught it while it was still inbound, which gave us months to study it as it approached the Sun. Telescopes all around the world were pointed at it. We were able to get detailed spectra, track its brightness and light curves, and build a comprehensive picture of its behavior. That is the ideal scenario. With 3I Atlas, we also caught it relatively early. We are getting good data now. But soon, it will reach its perihelion, make its tight swing around the Sun, and begin its long journey back into the darkness. And then, it will be gone forever. Unless we go to it. This is the next great dream of planetary science. Interstellar Object Intercept missions. There are now serious proposals being developed by space agencies for spacecraft that are specifically designed to launch, quickly accelerate to incredible speeds, and rendezvous with an interstellar visitor while it is still within our reach in the inner solar system. The technical challenges are, of course, enormous. You would need a spacecraft essentially on standby, a rapid response probe ready to launch on very short notice. You would need an incredibly powerful propulsion system to have any hope of matching the object at tremendous velocity. And you would need a suite of sophisticated instruments capable of analyzing its composition, its structure, and maybe, just maybe, even collecting a physical sample. But the scientific payoff would be beyond extraordinary. Imagine it. Landing on the surface of an interstellar comet, drilling down into its pristine ancient ice, collecting a sample of rock and dust that formed in another star system, and bringing it back to Earth for analysis in our most advanced laboratories. The science we could do with that material is almost unimaginable. We could determine the precise isotopic ratios of its elements, which would tell us about the specific nuclear processes that occurred in its parent star. We could analyze its complex organic molecules in ways that are simply impossible to do with a telescope from millions of kilometers away. We could search for amino acids, for prebiotic chemistry. We could even, if we were incredibly, unbelievably lucky, search for the fossilized remains of microbes. Even if we don't find life, we would learn about the chemistry of an alien planetary system in the most exquisite detail imaginable. Every molecule, every mineral grain, every isotope would be a clue, a word in the message it carried. This isn't science fiction anymore. These missions are being actively planned. Concepts exist. Budgets are being proposed. It is a problem of engineering. Hard engineering, to be sure, but doable. In 50 years, maybe 100, we might have a catalog of hundreds of interstellar objects. We might have successfully intercepted a dozen of them. We might have returned physical samples from half a dozen. And with that treasure trove of data, we would finally have a comprehensive, galactic-scale understanding of how planetary systems form, how chemistry varies across the cosmos, and maybe, just maybe, how common the potential for life really is. 3I Atlas is a preview. It's a tantalizing glimpse of what's possible. It is showing us that interstellar comets are not just rare curiosities. They are common. They are everywhere. And they are carrying the information that we so desperately want. The unseen population is out there, tumbling silently through the dark, just waiting for us to find them. And we will. One by one, we will find them, we will catalog them, we will study them, and we will piece together the grand puzzle of our cosmic origins. The coming flood of interstellar visitors promises to transform our understanding of the galaxy. But the mystery of 3I Atlas isn't happening in a vacuum. It's important to zoom out, to look at the bigger picture, because this one strange comet is not the only weird thing happening in the world of astronomy right now. Not by a long shot. We are living in a peculiar and exhilarating moment in scientific history, an age where our instruments have become so powerful that we are detecting anomalies faster than we can explain them. It's an age of whispers, of strange signals and baffling objects that are constantly challenging our neat and tidy models of the universe. Consider the roster of high-profile cosmic mysteries we've already accumulated. There are the odd radio circles, those vast, ghostly rings of radio emission with no known origin. There are the fast radio bursts, those impossibly brief, millisecond-long pulses of intense radio energy that flash from distant galaxies, their physical mechanism still hotly debated. There is Tabby's star, with its bizarre aperiodic dimming patterns that are still not fully explained by dust alone. There was Oumuamua, the interstellar object with its anomalous acceleration. And now there is 3I Atlas, the comet with its impossible water production and its strange metal anomalies. And those are just the famous cases, the ones that have captured the public imagination. Behind them are dozens, perhaps hundreds, of lesser-known anomalies lurking in the scientific literature. Transient astronomical events that don't fit into any known category. Strange spectral features that appear in the light from distant stars and galaxies that shouldn't exist. Objects moving in peculiar ways that seem to defy a simple explanation. It feels like, wherever we look, astronomy is finding things that just don't quite make sense. And in a way, this feeling is new. For most of the 20th century, astronomy was a data-starved field. The process was slow and methodical. You would point a telescope at a single interesting object, take a photographic plate or a spectrum, and then spend months, or even years, carefully analyzing that one precious piece of data. Discoveries were rare. True anomalies were even rarer. When something genuinely weird did show up, it received the intense, focused scrutiny of the entire astronomical community because there wasn't much else competing for their attention. Now we are drowning in data. The automated surveys are generating terabytes of it every single night. Sky mapping projects are creating catalogs with billions of objects. Gravitational wave detectors are recording the violent mergers of black holes and neutron stars on a weekly basis. Radio telescopes are scanning the sky continuously, listening for any transient whisper. We are detecting more stuff than we can possibly follow up on in detail. And with a high volume of data comes a high rate of anomalies. It's a simple matter of statistics. If you look at 1 billion objects, even if only 1 in a million of them is genuinely weird, you are still going to end up with 1,000 anomalies. Of course, most of those will eventually turn out to be something mundane, instrumental artifacts, glitches in the data pipeline, or simple misclassifications of known objects. But some of them will be real. And sorting the genuine mysteries from the instrumental ghosts takes an enormous amount of time and effort. We have officially entered an era where anomalies are outpacing theory. We are finding things faster than we can explain them. And that is both an incredibly exciting and a potentially dangerous place to be. It's exciting because new, unexplained phenomena are the engine of scientific progress. They are where the real breakthroughs happen. The discovery of pulsars, of gamma-ray bursts, of dark matter, of dark energy, and of gravitational waves all started with observations that, at the time, made absolutely no sense. Anomalies are the cracks in our current understanding of physics, and it's through those cracks that the light of a new, deeper understanding can shine through. But it's also dangerous, because the hype cycles surrounding these anomalies can spin wildly out of control. In our hyper-connected world, every new anomaly gets immediately hyped by the media and on social media as a potentially revolutionary discovery. Alien megastructures, warp drive signatures, wormholes, evidence of dark matter interactions. The media loves these stories. The public loves these stories. And then, 9 times out of 10, or perhaps even 99 times out of 100, the anomaly gets explained by something far more prosaic. Dust clouds, instrumental noise, a previously misidentified known object. The danger here is a slow but steady erosion of scientific credibility. When people hear the phrase, "it might be aliens," a dozen times, only to be followed by the conclusion, "actually, it was just dust," a dozen times, they can start to lose their trust in the scientific process. They start to think that science is just a series of wild, unsubstantiated speculations. Or worse, they can double down on the more exciting explanation, deciding that the scientists must be covering something up. Tabby's star is the ultimate cautionary tale. When the alien megastructure hypothesis first made headlines, the public latched onto it with incredible fervor. Social media exploded. News articles, hungry for clicks, ran with the most sensationalistic headlines. And then, when the careful follow-up observations showed that the dimming was wavelength-dependent, meaning it was almost certainly caused by tiny dust particles, not large, solid structures, there was a backlash. Some people accepted the scientific explanation and moved on. But a significant number insisted that the scientists were wrong, or even that they were deliberately lying to hide the truth. But here is the crucial thing to understand. Even with the dust explanation, Tabby's star is still interesting. The simple dust model doesn't fully account for all of the complex, long-term variability. It's still a genuinely weird star, perhaps surrounded by a massive, clumpy debris disk from a recent planetary collision, possibly doing something we don't entirely understand yet. It's still great science, still a valuable mystery. It's just not aliens. The lesson from all of this is that anomalies are opportunities. They push us to refine our models, to consider new physical mechanisms, and to challenge our most basic assumptions. Even when they don't lead to a revolution in physics, they always advance it. Oumuamua's anomalous acceleration, even if it was just outgassing, forced cometary scientists to think much harder about sublimation processes at very low temperatures, about the properties of exotic ices, and about the surface physics of interstellar objects. That is real progress. 3I Atlas is another one of these incredible opportunities. Its impossible water production is challenging our understanding of volatile activation distances. Its nickel anomaly is forcing us to think about metal chemistry in comets, something we've largely ignored in the past because our own comets don't show strong metal emissions. Its carbon dioxide dominance is opening up a whole new window into the conditions of protoplanetary disks in other star systems. When you begin to stack enough of these anomalies on top of each other, sometimes larger patterns can begin to emerge. Maybe the odd radio circles and the fast radio bursts are, in fact, related, both stemming from some kind of energetic outflow from the centers of galaxies. Maybe interstellar objects like Oumuamua and 3I Atlas represent two completely distinct populations, formed through different mechanisms in different types of star systems. Or maybe they are all just completely unrelated individual quirks of the cosmos that we just happen to be discovering in the same few decades because we finally have the technology to detect them. Either answer is incredibly informative. The key, for all of us, is to try to maintain a delicate balance between skepticism and wonder. You can be excited about an anomaly without immediately claiming that it is going to rewrite the laws of physics. You can investigate the weirdest, wildest possibilities without becoming emotionally wedded to them. And most importantly, you can be willing to change your mind when new evidence arrives. This is where good, responsible science communication matters more than ever. The solution is not to stop reporting on these fascinating anomalies. The solution is to be honest about the uncertainty, to present the multiple hypotheses, and to treat the public like intelligent adults who can handle the ambiguity of the scientific process. 3I Atlas is one more anomaly in a growing stack. It's a hugely important and fascinating one. But it is not, as yet, proof of anything revolutionary. It is a data point. It is a mystery. And it is, above all, an opportunity to learn. So here we are. We have journeyed across billions of kilometers and billions of years, all in pursuit of a single ghostly green comet. We have contemplated its impossible torrent of water, its strange, lonely nickel, and its choreographed dance of awakening. We've considered its ancient origins in a long-dead star system and the alien chemistry it carries in its heart. After all of this, we are left with the ultimate question, the one that has been whispering beneath the surface of this entire story. Is this thing alive? In a poetic sense, perhaps it is. It is dynamic. It is changing. It is actively responding to its environment in the most dramatic fashion. It is awake and alive with activity in a realm where it should be cold, dormant, and dead. Its behavior feels so purposeful, so deliberate, even though we know rationally that it is being driven by the impersonal laws of physics and chemistry, not by any conscious intention. But alive in the literal biological sense? Almost certainly not. There is no evidence of biology here. We see no signs of metabolic processes, no hints of reproduction, no complex information storage and transfer systems like DNA. We see none of the fundamental hallmarks of life as we understand it. At its core, 3I Atlas is a rock. A very special rock, covered in exotic ices, being gently heated by the distant light of our sun, which causes it to release gas and dust according to a set of physical laws. And yet, those very same physical laws are producing something that we have never, ever seen before. Water sublimation at unprecedented distances, nickel decoupled from its iron twin, a stunning dominance of carbon dioxide, a switch-on behavior that suggests an incredibly complex internal structure, or the presence of exotic ice compositions that we've only dreamed of. Every new observation, every new piece of data simply adds another layer to the beautiful, intricate puzzle. So, what is it? When all is said and done, the most likely explanation is also the most elegant one. 3I Atlas is a natural comet, but one that was formed under a set of conditions that were profoundly different from those that existed in our own solar system. Maybe it was born much farther out from its parent star, in a frigid region where carbon dioxide ice was far more abundant than water ice. Maybe its parent star was born from a cloud of gas that had been seeded by a very unusual mix of supernova, leading to its strange metal ratios. Maybe the eons it spent wandering through the harsh radiation environment of interstellar space fundamentally altered its surface chemistry in ways we are only just beginning to comprehend. That organometallic hypothesis, where the nickel was trapped inside volatile molecular cages, remains an incredibly intriguing possibility. It would require a very specific set of chemical conditions during its formation, but nothing that is physically impossible, just unusual. And the idea of its origin in the ancient thick disk is still the most compelling of all. If 3I Atlas is truly 7 billion years old, if it is carrying the isotopic fingerprints from an earlier, chemically primitive era of our galaxy's history that could elegantly explain many of its oddities, we would be looking at ancient ice, ancient chemistry, and ancient minerals, all perfectly preserved in the deep freeze of interstellar space. and now, finally, being revealed to us as the comet warms in the light of our sun. Could it be artificial? Could it be a probe, a derelict spacecraft, some kind of technological artifact sent from another civilization? The evidence simply does not support that conclusion. There is nothing about 3I Atlas that requires a technological explanation. Everything we are seeing can be explained, or at least can be potentially explained, by natural physical processes. Invoking aliens is an unnecessary leap, a violation of the scientific principle of Occam's razor, which tells us not to multiply entities beyond necessity. But let's allow our imaginations to run free for just one final moment. If you wanted to design a probe that could survive a journey of billions of years across interstellar space, and still be detectable by a curious civilization billions of years later, how might you do it? You would probably want to use a natural, comet-like object as a protective shell, shielding your precious payload deep inside with meters of ice and rock. You might even want to deliberately include some unusual chemical signatures, some strange metallic markers that would stand out to anyone who bothered to analyze its spectrum. You would let the natural process of sublimation do the work for you, revealing those markers as the object approached a new star. This is, of course, the purest speculation. There is no evidence for it, but it is worth noting that if we ever do encounter a genuine artificial interstellar object, it might not look like a gleaming starship at first glance. It might just look like a comet. A very, very weird comet. 3I Atlas is almost certainly not that object. But the very fact that we are even asking the question, that the comet's behavior is strange enough to stretch our imaginations to such limits, tells you something important. It tells you that this object is a gift, not because of what it is but because of what it does to us. It makes us think. It makes us question our most fundamental assumptions. It reminds us, in the most visceral way, that the universe is bigger and stranger and more wonderfully creative than our tiny little corner of it has led us to believe. It reminds us that nature has had trillions of star systems and billions of years to explore the vast, multi-dimensional space of what is chemically possible. And we have barely begun to survey the coast of that great, unknown continent. Every interstellar visitor is a challenge. It challenges our models, our theories, and our ingrained sense of what is normal. And it is through facing these challenges that we grow. Oumuamua challenged our understanding of cometary activity. 2I Borisov challenged our assumptions about carbon monoxide abundances. And 3I Atlas is challenging everything. Our models of volatile budgets, of metal chemistry, of activity distances, of compositional diversity. The next steps in this grand adventure are clear. We must continue to watch 3I Atlas as it makes its closest approach to our sun. We must measure everything: its spectra, its light curve, its gas production rates, its dust-to-gas ratio. We must look for new emission lines, and we must watch intently to see if the iron ever finally appears, or if the nickel anomaly persists, a stubborn testament to its alien origins. We must compare our observations to our models, refine those models, generate new predictions, and then test them rigorously. And above all, we must prepare for the next interstellar visitor, because there will be another, and another. The galaxy is full of these wanderers, and our technology for finding them is getting better every single year. Each one will be a new puzzle, a new set of clues, a new window into the grand tapestry of how planetary systems form and evolve across the breathtaking diversity of stellar environments. Maybe one day, we will intercept one. We will land on it, drill into it, and bring its secrets home. Until then, we will do what humans do best. We will watch. We will measure. And we will wonder. We will look up at the universe, and we will ask questions. Why is that comet active so far from the sun? Where did it come from? What can it teach us? The questions themselves are valuable. perhaps even more valuable than the answers. Because questions are how all exploration begins. 3. Atlas came from somewhere out there, a place we can only dream of, carrying a message written in the language of water and nickel and cyanide. We didn't ask for this message. We don't fully understand what it says yet, but we are listening. We are watching. And we are learning. And in that simple, profound act of learning, in that stubborn, human insistence on understanding, we find the one thing in this entire story that might be the closest thing to truly being alive. It's not the comet. It's us. Curious, wondering, constantly reaching out to touch something that came from impossibly far away, trying to read a letter from another world. The universe keeps sending these letters. And every time one arrives, we are reminded that we live in a vast, ancient, and incomprehensibly rich cosmos. A cosmos that will forever outpace our understanding, forever surprise us, and forever offer us new and more beautiful mysteries to solve. 3i, Atlas is one of those mysteries. But it's our mystery now, and that is a wonderful thing.